Hello everyone, I hope you're all staying safe. We're going to continue from where we left off in the previous concept talk. I'm going to look at the velocity and the acceleration vectors once again, briefly summarize what's going on there, and then we will move on to the idea of rectilinear motion or motion along a straight line. Okay, so from before, we have the following. We have the velocity vector given as v is dr by dt, and then the direction of the velocity vector is always the same as the direction of the displacement vector, and both of these are tangent to the path at any point in time, right? And the direction of v is the same as the direction of dr, and they are both tangent to the path of the particle at time t. And this essentially is nothing but the velocity at time t. Okay? And if we had to draw a figure for this, we said that okay, if this was the general path of the particle, and if the particle is sitting here, if this was like p of t, then I could say that okay, here is the tangent to the path, okay, and this is the unit vector e suffix t in the direction tangent to the path, okay, and using that I could write the following. The velocity vector v is the magnitude of dr by dt multiplied by the unit vector along its direction, which is e suffix t, okay, and dr by dt, the magnitude of dr by dt, as you know from before, is nothing but ds by dt, okay, so which tells me that the velocity vector v is ds by dt times e of t. Okay, this is an important result and I'm going to box it up. And something that we will keep revisiting again and again and again. And the key takeaway is so far is that the direction of velocity vector v is tangent to the path of the particle at any point in time t, and this is given by e suffix t. Okay, the direction. All right. Then I said that okay, we will look at the direction of the velocity acceleration vector as well. Okay, so I look at the acceleration vector. Okay, if I do that, what do I get? We know from before that the acceleration vector is the rate of change of the velocity vector. Okay, so we know that acceleration a is dv by dt. Okay, now I'm going to substitute for v from the expression above. Okay, so which tells me that a is going to be d by dt of ds by dt times e of t. Now, ds by dt is a quantity that changes with time. E of t is also a quantity that changes with time. This is quite obvious for you to see, right? Because you see, go back to my path here. If I look at this point here, the direction of the unit vector is going to be in the following manner. If I look at the point here, the direction of the unit vector is going to be in the following manner, right? And these are all the directions of e of t at different points in time. And so the direction of e of t keeps changing over time. Okay, so something to note here is that the quantity ds by dt can change with time. Then the quantity e of t can also change with time. Which means that if I'm looking at the acceleration vector, then I have to use the product rule and say the following. Okay, so product rule of differentiation. And that's essentially using the product rule, I get acceleration A. Okay, use this on there to differentiate and get the following. So this is going to be d by dt of the first quantity, ds by dt times e of t, and then I'm going to have ds by dt times d by dt of e of t. This is very interesting, and I'm quite sure that you may not have come across these things in your introductory physics courses. Okay, now ds by dt, I can write the expression as the following. So I can say that this is acceleration A is d square s by dt square times e of t plus ds by dt times this quantity d by dt of et, which I'm going to leave it as it is for the time being. Okay, but we will eventually reduce it to the following form later on. Okay, now ds by dt is the speed v. Okay, this is one way of writing the acceleration vector. So another way, ds by dt is equal to v, which means that d square s by dt square is the differentiation of the speed, is the rate of change of the speed, right? Which means that the acceleration vector A can be written as dv by dt times e of t plus v times d by dt of et. Okay, this is another way of writing the acceleration vector. I'm just going to underline some of these things. So there is one way of writing it. Then there is another way of writing it, which I have written down below here. Okay, so this is the other way of writing the acceleration vector. Now, for the people who are curious, we can say the following about d by dt. Okay, so we will derive this later on. So from later we will derive d by dt of et can be written as v by rho. Okay, this is the velocity or the speed, I'm sorry, divided by the radius of curvature of the path. Okay, okay, this is going to be the quantity rho, and this is going to be the quantity v, which is that. And if I do the substitutions, right, then in a much nicer form, we will obtain the acceleration A as dv by dt et plus v times v by rho, and I'm sorry, I obtain the magnitude of this quantity as that. Okay, and the direction of that quantity, the rate of change of the unit vector, will be given as e suffix n, which is the unit vector normal to the tangential vector. Okay, this is something that we will be deriving later. Okay, and then so the acceleration vector is going to be dv by dt et and v squared by rho en. Okay, this is not information that is used right away. All right, and when you look at it, what is the direction of the normal vector? Very, very quickly is that the normal vector is always going to be pointing towards the concave side of the trajectory, and it's going to be perpendicular to the unit tangential vector. Okay, these are all local vectors, which means that they're all going to be changing with time. Okay, so this is going to be en, this is going to be en, and this is going to be en as well. Okay, so these are all different ways of writing the acceleration vector, just in case you missed out seeing the en. And in this case also, it's going to be pointing inwards towards the concave side of the trajectory. We will see why that is the case later on. Okay, this is not something we need to worry about right now. Okay, so I want to underline one more thing as well, right? That's the way we have written the acceleration here. So that's also another way of writing the acceleration vector. So in summary, I have the following: the velocity vector. So in summary, velocity vector v is going to be ds by dt times et. Now this ds by dt can be written in a shorthand notation as s dot. Okay, this is called the dot notation of writing the first and the second time derivatives. So first time derivative one dot on the quantity. Okay, then if you have two time derivatives, then it's going to be two dots on the quantity. Okay, so s dot here represents ds by dt. Okay, this is one way of writing the acceleration, a velocity vector, something that I typically prefer as we go on further down the course. Okay, when we study about equations of motion and so on. And then the acceleration vector is a, which is dv by dt times et plus v squared by rho times en. And if you want, if you're more comfortable, you can also write it in the following manner. So a is dv by dt et plus v times d by dt of e suffix t. Okay, both of them are fair game. And I can make use of the same dot notation. So this is called the dot notation. And the dot implies time derivative or derivative with respect to time. Okay, so which means that my acceleration vector can be written as v dot et plus v times e dot of t. Okay, these are all key things that we will keep coming across quite often. Okay, now what's the nice thing here? The nice thing here is the following. What is the direction of the velocity vector? It's always tangent to the path, right? Because it's in the direction of et. But what is the direction of the acceleration vector? It is not necessarily tangential to the path if the path of the particle is a curved path. Okay, so this tells me that the direction of the acceleration vector is not necessarily tangent to the path if the path of the particle is a curve. But if the path of the particle is a straight line, or rectilinear, then I can say that E dot of t is equal to 0 because it is just traveling along a straight line, right? Then the tangential vector is not going to change with respect to time. And so in rectilinear motion, I have the following nice things happening to me, making my life a little more simpler. Is that first of all, velocity is as before. This is going to be ds by dt times et, and then the acceleration vector is now going to be dv by dt times et, which means that the magnitude of the velocity vector, which is called the speed, okay, v is just going to be ds by dt, and then the magnitude of the acceleration vector, which is just going to be called the acceleration, is a, is dv by dt, or you can write this as d square s by dt square. Okay, and when I look at the acceleration vector, I make use of what is called as a chain rule once in a while to write the relationship in a nicer way. Okay, so I can make use of the chain rule of differentiation. Okay, I can say that the acceleration is dv by ds times ds by dt, right? This is fair game, right? Because if you think of these as ratios, then I can cancel off the ds and the ds, and this is the same as dv by dt. But you know what? ds by dt is v, which tells me that a is v dv by ds. And this is an important thing that we will keep doing again and again, the chain rule of differentiation. And previously we had used the product rule, if you remember. Okay, so rules of differentiation is something that you need to know pretty well, and I'm sure you've come across this in your basic math classes. Okay, so in terms of a summary of rectilinear motion equations, okay, so summary, rectilinear motion. Okay, here are the terms that are involved. Velocity v is ds by dt et, and acceleration is dv by dt et. But because I'm traveling along a straight line path, I'm not really interested in the unit vector along that path. Who cares, right? Because I know what the unit vector is, right? Which means that I'm mostly interested in the speed and the acceleration. How does the magnitude change? Does the magnitude increase or decrease? And the increase or decrease is going to tell me whether the velocity is traveling along the path or opposite to the path. Okay, the opposite is a straight line path. Okay, so which means that the other relationships that we will be making use of are these speed v, which is ds by dt, then acceleration a, which is dv by dt, and then I'm going to have the chain rule relationship for the acceleration. A is dv dv by ds. Okay, these are the key things. And one last statement before I move on. Okay, so in rectilinear motion, which means that I'm essentially traveling along a straight line path. Okay, I'm going from point A to point B. So travel along a straight line, that is rectilinear motion. So since we already know the direction of travel, we are more interested in the magnitudes of the velocity and acceleration vectors. Okay, and the magnitude change, it could be positive or it could be negative. Then using the magnitude change, we can understand whether the velocity is along the path or opposite to the direction. Okay, so that's essentially it for rectilinear motion. And there are some derivations that I'm going to offload onto my more elaborate notes. But what I'm going to do is I'm going to make use of all these relationships that we've come up with here. Okay, all these terms that you see in the summary for rectilinear motion, and I'm going to make use of each one of them and try to solve short worked out examples where we see, okay, how am I going to make use of these equations to understand what the kinematics of the particle is. All right, thank you very much, and I hope you all stay safe. Bye bye.